Hi, welcome back to everyone. So, okay, this is the second part of FM lecture, where we look at the generation and also the detection of FM signals, and also some practical um, uh, characteristics of FM receivers. Okay, so before I start, again, we not discuss, just to expose you to the previous final year exam questions on angle modulation or FM for focusing on the second part, the generation and detection or demodulation and demodulation circuits. Okay, so if you look at, I've compiled here a number of semester's final exams questions. Okay, for session 2014-15, semester 1. Okay, sorry. Okay, if you look at the question, here FM has found wide application in the area of radio broadcasting, replacing the early AM radio. Advantage and disadvantage of using FM instead of AM in this context. Okay, so the advantage of FM, we have already discussed in our first part of today's lecture, yeah. And the disadvantage of FM, what are they? Can you think of? Right. So one of them, the most obvious, yeah, you can see that it uses more bandwidth. Yeah. Main drawback of using stereo instead of mono FM's transmission. Okay, this one we will learn, yeah, in the second part of FM lecture. The detection. So here you have mono, stereo, and then next draw block diagrams, and then explain or describe the operation of FM stereo. Okay, so this is one type of FM receiver that you have to pay close attention to, FM stereo versus mono. And then over here, you see, okay, you're given list of components in the table, and then list of components in the table. Okay, you're approached by an engineer, okay, for consultation. So this engineer wants to design FM transmitter with operating frequency at 104 megahertz and frequency deviation 75 kilohertz. Okay, so given all these components, you need to draw the block diagram and value for each component. Okay, so this actually belongs to the wideband FM generation. So how we can tell from the frequency deviation. So the narrowband frequency deviation is not as high as this. So in 75 kilohertz belongs to wideband FM. Okay, and then 104.1 is where the frequency of another FM transmitter. Okay, discuss possible effects if we operate them simultaneously. So this is so you need to know lah, what's the deviation, whether the deviation between these two operating frequencies can cause interference or not. If you put them closely at these frequencies, 104.1, what will happen? Okay, so this is wideband FM. Another one, okay, you design a wideband frequency modulator using Armstrong method. Okay, so you can hear, no, here you're introduced to new term, Armstrong. Okay, what is Armstrong method for FM generation? So we learned this in our lecture. Then wideband FM, draw wideband FM block diagram. Okay, so again for this year on wideband FM. Okay, this is semester 1. Semester 2 also narrowband to generate wideband FM. Okay, again wideband FM signal. And then after that, 2018-92 illustrate a super heterodyne FM receiver. So it's super heterodyne. Okay. 1 year after that, describe two principles of demodulating a frequency modulation signal. Okay, what are these two methods? Okay, so we learned this. And then, okay, session 2019-21. Okay, again, you can see it's FM stereo. We've already go through this. And then super heterodyne FM receiver again. Yeah, it's almost similar to the other question, but the operating frequency is different. Okay, so those are the some examples of final year exam questions that address what we will learn in the second part of FM chapter. Yeah. Okay. So hopefully you'll be able to grab the highlights of those questions. And okay, we'll continue with generation of FM signal. Okay, so there are two techniques to generate FM signals. Okay, direct and indirect methods. So for basically to generate FM signal, we need a system that enables the frequency of the output signal to vary in accordance to an information signal's amplitude. Basically, it should be proportional. The frequency of our output signal is proportional to the information signal's amplitude that will be our input to the system. Okay, so direct methods are methods that use approaches like using varactor diode, reactance modulation, and voltage control oscillator. So in all these methods, output frequency of all these devices is proportional to the input voltage. Okay, if you look at the first approach using varactor diode, okay, so first we look at the characteristic of varactor diode. Okay, we can see that okay, for voltage, okay, on top is a voltage, and then here's our capacitance value. So the capacitance value, the reverse voltage applied changes our capacitance value. Okay, so in other words, varactor diode's capacitance depends on the voltage across it. Okay, so we know that capacitance is a function of our frequency. Okay, so if we put input such as audio signals across this diode, it can cause the capacitance to change, and accordingly our frequency of our oscillator will also change. Okay, so the output of FO here is our output frequency, and so the output is equal to 1 over 2 pi square root of LCT, okay, where this CT is equal to C naught plus C. So C naught is the value of our capacitance when Vm equal to 0, meaning that when there's no input signal, so F out is equal to FC. FC is our reference frequency, which is equal to 1 over 2 pi square root L C naught. Okay. And C is the capacitance, variation is the value when we apply our information voltage. So C is equal to kVm, where K is the variable and Vm is the information signal's voltage. Okay, so C is the where we have the influence of Vm to our capacitance. So if we substitute Ct equal to C naught plus C inside this FO equation, so we got 1 over 2 pi square root L times C naught plus C. And then we factor out the C naught, and then factor out C naught, and then becomes 1 over 2 pi square root L C naught times this one 1 plus C over C naught, to the power of minus half, because we brought this up, okay, the square root. So it becomes minus to the power of minus half. So if you notice, this is our FC, 1 over 2 pi square root LC naught. So this is our FC. So this is the frequency without modulation. Okay, so the term 1 plus C over C naught to the power of minus half can be represented based on binomial expansion, which is 1 over C over 2 C naught, if C over C naught is small. So by assuming this relationship, okay, F out is then equal to FC times 1 minus C over 2 C naught, from here to here. And then C is equal to KVM. So if you put KVM here, then this is our output frequency, okay, where you can see from this equation that our output frequency is in function of our modulating signal's amplitude. So this is one way of showing through mathematically how we can produce F out that is changed in accordance to our VMT. Okay, so I hope I'm not too fast. Okay, so for the other methods such as reactance modulator and VCO, the concept is very similar. If vector diode using diode, so reactance modulator, it's using transistor. Okay, so if we place our modulating signals at the input of our reactance modulator, the modulator's reactance will vary in response to the applied information signal. So this will also change our oscillator's frequency. Then the same concept for VCO as well, where the VCO's output frequency is changed proportional to the voltage of our input signal. Okay, so these are examples of direct method of generating FM signal. Okay, so using direct method, there's an issue of frequency drift. Okay, because the produced frequency is not stable, so it's subject to some errors. Okay, so in order to overcome this problem, we in Crosby FM generator is introduced. Okay, so what's new with this Crosby circuit is that the incorporation of AFC, automatic frequency control. Okay, so the idea is to give a feedback in terms of error control voltage to the modulator. Okay, so if we set at the so it uses a crystal oscillator to produce a highly stable frequency. But we cannot change the frequency of these crystal oscillators directly. So it is used as a reference to our AFC circuit. Okay, so and then this frequency difference or error will be sent to discriminator that produce error voltage. Okay, so discriminator in principle works in opposite to VCO. If VCO produce voltage control frequency, meaning that frequency that is changed according to voltage, discriminator produce frequency control voltage, where it produce voltage that is changed by the frequency. Okay. Okay, so this is the block diagram of Crosby FM generator. So here is our direct FM direct FM circuit. So using reactance modulator, so input and then to antenna. Okay, see here, we have the additional AFC circuit for frequency stabilization. Okay, where we have our crystal oscillator and the F out from the reactance modulator as inputs to our mixer. So from these two, it will produce this delta F, which is the frequency difference between the one that we want and the one that produced. Okay, so this delta F error frequency is fed into our discriminator, and this discriminator will produce error voltage in accordance to our delta F. So this error voltage will be sent to reactance modulator, and it will be from the error voltage here, the reactance modulator will also produce frequency accordingly to fix the frequency drift. So when difference between them is 0, then only there's no more frequency error, and accordingly frequency voltage also 0. So this is to overcome the frequency drift issue in direct FM generator. So it's known as Crosby FM generator. Okay, the maximum deviation is around 5 kilohertz, if we use Crosby. So actually for commercial wideband FM, like the radio FM, the radio FM station, so the frequency deviation is used is 75 kilohertz. Okay, so because of the low maximum deviation in direct FM method, we need to apply frequency multiplication. Okay, so this frequency multiplication will multiplies the input signal. So by doing this, the modulating signal, the FM, is not changed, but the carrier's frequency and the deviation and also the modulation index are multiplied. Okay, but the FM is unchanged. Okay, so here is an example of if we have multiplier in our circuit to increase our deviation, and also normally the operating frequency for direct FM is also not very high, so that's why we use multiplier to increase the operating frequencies too. Okay, so in this example, we have this FM station operates at 106.5 megahertz, deviation 75 kilohertz. So FM signal originally is generated by a reactance modulator. So it operates at this frequency 3.9444 megahertz with deviation around 2.08 kilohertz. Okay, so this is output. Okay, our input to our Crosby FM generator, and then output of Crosby generator. It's one with operating frequency 3.94 megahertz and deviation around 2.8 kilohertz. Okay, so how do we increase our frequencies so that it matches the wideband frequencies and also the wideband deviation? So if you look, if we multiply by the same factor, so in order to simplify the explanation for this explanation of wideband, we choose so that the value so that one factor can multiply both F and delta F. Okay, so in this example, we just use one frequency multiplier with factor 27. Okay, so when we multiply F times 27, we got 106.5 megahertz, then 2.8 kilohertz times 27, we got around 75 kilohertz. Okay, so here it says that the resulting FM signal is fed through 3 frequency triplets. Okay, so normally, practically, we don't have very multiplier with very high value, because when you have very high values, okay, there's this problem of issue of harmonics. If I'm not mistaken, high harmonics. So normally, instead of using one multiplier with very high factor, they use smaller, smaller multiplier times 2 or times 3. So it's called doubler or tripler, and then this doubler or tripler will be combined in order to increase the factor. Okay, for example, in this 27, we can produce this multiplier with factor 27 by using 3 frequency triplets in series. So it's 3 times 3 times 3 equal to 27. Okay. All right. So this is an example how we change from the narrowband FM to wideband FM using multiplier. So, okay. Next is using indirect method. So with indirect method, you notice this keyword Armstrong, that we saw this word first in the final year exam sample I showed before. So with this indirect Armstrong method, okay, we generate FM signal using phase modulator PM. Okay, so even though it's not that possible to directly vary the frequency of crystal oscillator, okay, so it's possible to directly vary its phase. Okay, so we vary its phase, so it becomes phase modulator, and this phase modulator is used to generate FM signal, provided that we use the integration of our VMT, or integral of our input signal. And if you combine these two, integration of VMT to our PM, then we produce FM signal. So this is an indirect method of generating FM. Since the carrier source using crystal oscillator is already stable, so there's no need for a AFC loop. Okay. However, there's one issue using this indirect Armstrong method, which is the deviation is very small, just in hertz compared to direct FM in kilohertz, but this one is even worse in hertz. So it's not suitable for wideband FM. Okay, so using only multipliers is not enough. We have to combine with mixers. Okay. So this part I will explain not today due to time constraint. For the wideband FM using Armstrong method, I'll explain in our next class on Wednesday, inshallah. Okay, I'll just explain first the generation of narrowband FM using Armstrong. Okay, so this is our phase modulator part, and this is our integration of VMT. Okay, so we can look mathematically, we can refer to the equation of narrowband FM signal. Okay, first let's refresh some concepts that we have learned in our last lecture, okay, last week. So this is our frequency deviation, which is equal to KF VMT, and the phase deviation is KF integration of our VMT dt. Okay, assuming our VMT cosine then become beta sine omega mt. And for narrowband FM, beta sine omega mt is much less than 1. Okay. So similarly, then our phi-CT, phase deviation, is also much less than 1. Since phase deviation is equal to beta sine omega mt. Okay, so we start with the general equation for FM signal. So it's EC cos omega C plus phi-CT. Okay, and then we expand using cos A cos B. again, this we already you were introduced to this narrowband FM concept in last week, so we just refresh. Okay, here since cos omega phi c t is much less than 1, then cos omega cos phi c t is approaching 1 and sine phi c t is approaching phi c t. So this is our narrowband FM equation before we expand using sine A sine B. So we got EC cos omega CT minus phi CT EC sine omega CT, where this phi CT is equal to beta sine omega MT or KF integration VMT, yeah, from here, okay? KF integration VMT dt. Okay, so we can actually draw a block diagram based on this maths. Okay, so here is our KF integration VMT dt. Okay, so this phi CT will multiply with EC sine omega CT, and then plus, and then the minus of this term will be add to EC cos omega CT. So here you can transform this into block diagram. So we have our EC cos omega CT plus here, then another one minus over here. Okay, so this is the part where we have our phi c t EC sine omega CT. So here we apply 90-degree phase shift, so it becomes EC sine omega CT. Then we multiply with phi c, becomes phi c t EC sine omega CT. So this is phi CT, EC sine omega CT, and then we have minus. So the output then will be similar to this equation, yeah. So where our phi c is KF times integration of our VMT dt. Okay, so this part basically just to show you how we can use phase modulator circuit to generate narrowband FM signal. Okay, and if we want to convert, so remember indirect FM from narrow band to wideband, we use multiplier. And for this indirect, we also need to convert from narrowband to wideband, because the practical or the commercial FM, the FM applications are based on wideband. So our narrowband FM then will be sent to frequency multiplier and mixer. Okay, so the function of frequency multiplier, like I said previously, increase the frequency deviation, modulation index, and also the operating frequency. But the FM does not change. Okay, so apply the mixer here in order to reduce the carrier's frequency. Because when we apply this multiplier, if we apply this frequency multiplier, when our delta F is very small, then the operating frequency can be very, very high, much high. So that's why we need a mixer to downgrade the operating frequency. So if you notice, this part is quite popular in final year exam questions. I've seen a number of questions asking for this wideband FM block diagram. Okay. All right, so for the wideband FM part, I will not discuss today, because we don't have much time. So we stop today at indirect FM using Armstrong, and then inshallah this Wednesday we continue with wideband FM, and the demodulation circuits, and also FM stereo and super heterodyne. Okay, that's all for now. And don't forget, anything, any feedback, comment, questions, just drop in the Google Classroom post and also Telegram. You can choose either one. Okay, that's it. Assalamualaikum and see you again this Wednesday. Bye-bye.